This is my bushfire resistant tiny house, number 3. This is very highly fire resistant. The others were to a medium level. These are some of the materials that we're going to be testing today. I'm going to be setting them on fire as much as possible. The conditions of these tests are that the temperature was about 30 degrees when I started, um, and we're using an LPG flame 1900 degrees. That's a piece of 9mm ply. Obviously a lot of flame coming off it. The key here is the heat transfer to the inside, and to test that I'm using a piece of wax which will melt at about 60 degrees. The flame is also, this footage is in double time as well. So about to call an end to that test. Wax was fine. And the underside obviously pretty charred and unstable too. It's done a lot of movement. This is the exact same material but with fireproof paint on the underside. It's Fire Shell F1E, 2 coats. And you can see we don't have the flame bursting off the sides like we did on the first one. Missing a blob of wax just at the second, there it is. This paint performs very, very well. Really impressed with it. It's been used for arson proofing as well as bushfire. It's rated to a BAL 29 level when you put it on top of pine. It is expensive, but sometimes the best way is particularly to get around a retrofit. It can also provide a very light cladding for a tiny house which is weight limited. Starting to get some melting of the wax on top there, but that was super impressive. That went for about 4 minutes, that test. And didn't necessarily have to call an end to it really, it's just kind of pointless. You can see there the timber is still fine on the underside. The puffing up of the paint has protected the timber really well. So another timber board, that's spotted gum. You can see the amount of flame coming off the underside there. That's an impressive torch I'm using. It's at 140 psi coming out of an LPG bottle. So main problem here is that I constructed this in too much of a hurry. And that panel, which goes all well at the beginning, is about to fall apart due to the glue. I didn't take the time to put mechanical fixings in, such as screws. And the glue was still pretty fresh. It's about 4 hours old at that point. So there's one bit dropping off the side there. The wax stayed intact. That wasn't a problem. The heat transfer through timber, again, really good. It's quite a good, look at the wax is just untouched. The timber's pretty charred on the other side, but it doesn't go through very far. And the timber, each board at least, is still very stable. So as long as you've got this joined together well, they can make a pretty good shutter. Just some steel. So this is actually not steel, that's aluminium. That we're testing. It's checker plate, so it's 2.5mm checker plate. Still rated for the use in windows. It's aluminium at really high fire ratings, which is concerning. That is the melting point. It's about 360 degrees. That's why you don't want to use aluminium on your fire-resistant house. Also want to be conscious, aluminium gets used in a lot of places, including rivets, and we'll see what happens to those later. Gave up on the wax blob. Some of these materials, interestingly, expand upwards, and some of them expand downwards. So interesting to see the ways that the materials went. This is a steel sheet. It's 2mm steel. It's very similar to what I've used on the tiny house behind me. It's not checker plate. It's just regular flat steel sheet, mild steel. It's got a nice bowed curve to it, but the curve, the expansion, the stability of steel is the problem in a fire. It looks good. It doesn't combust. This is how it needs to be used, though, in conjunction with something else. So this is possible. Instantly, we haven't got flame coming off, obviously, because it's on steel, so opposed to the timber shutter that we saw, or the timber panel. And it's staying flat. We're not getting the big bow that we saw from the steel sheet on its own earlier. big problem here is the smoke, and some of that's coming mostly from the glues and silicon that was around the edge. Um, Again, not entirely happy with my test. I hope to reproduce this one in the future with a bit more time. Um, but to see that other than the warping on top, it actually stayed. It probably did its job. That that shutter, if that was on the outside of the door, that probably did its job. It stayed flat. Now this is a magnesium board. This is a different material altogether. Um, it's obviously a fire resistant material, and it works well. The heat transfer through to the inside from a 12mm sheet um, wasn't as good as timber. 9mm pine was actually better than the 12mm magnesium board for heat transfer. You can see it wax, there it goes. Wax is melted on top there. So um, it is, of course, an extreme test. This material is obviously much better for heat transfer than just steel. Um, but again, really needs to be used in conjunction with timber or with insulation, a good amount of insulation to stop heat transfer through to the inside of the house. But it's definitely a good start. It stays very stable. It doesn't ignite. Um, all in all, a pretty good cladding to use on the outside of your house. It's relatively light, so I do use it on tiny houses. It's it's relatively easy and simple to work with as well. It takes screws, can be cut with a circular saw. So I'm generally a fan of this product. See, obviously, yeah, we're getting a fair bit of heat transfer, and eventually some of the surface popped off there. But anywhere that didn't have the precise gas flame on it stood up to the flame very well. We didn't see an enormous amount of charring, only in one spot there. Mineral wool insulation. This is a Bradford product, similar to Rockwool, which is the more commonly known product. This performs really well. You can see it's staying relatively stable. It's got a bit of a twist at the back there, and it's also expanding, but generally very good. What I'm trying to achieve with my tiny houses, particularly because they're so small, is to stop the transfer of heat through to the inside. If the inside heats up more than around 100 degrees, you risk electrical fault, which is, your electrical system's only rated to 90 degrees. You also risk spontaneous combustion of fabrics, curtains, carpets, bedding, clothing, furniture, couches, are all liable to spontaneously combust and are far more flammable than anything that's on the outside of the house. So that's the main aim of my construction, is to try and keep heat on the outside. Flame contact obviously happens, and this house is rated for flame contact. Rated, it probably isn't the correct word. There's no rating for a tiny house on wheels, but it's designed to take flame contact. But usually flame contact lasts seconds, not minutes, as in this situation. And this product that we're looking at is not intended to have direct flame contact put on it. But having said that, if this is jammed into every orifice of your house, as it is on my design, then you're going to do pretty well on the fire. Often used in conjunction with steel, to stop the heat transfer, which is obviously a problem with steel. So this products like this can allow you to use tin cladding, corrugated iron, put it behind ridge caps, corner molds, barge flashings. So a product like this can allow you to use tin, which is relatively cheap and light. About to call an end to this test. The main failing, I guess, of this was some smoke that came through to the inside, but really, really small amounts. Most of the smoke you can see there is actually coming from the bottom, which is actually a timber block where my torch is sitting. Generally a very good test, very impressive. See a tiny bit of melt there starting to happen, but very good. It actually, yeah, surprisingly, bit of ignition, and it didn't just smudge out like I thought it would. Um, but largely very good, very stable. Um, and for a product which isn't designed to have direct flame contact, that certainly did the trick. This is predictable. Really common cladding and often considered to be fire resistant, and it can be, but not on its own. So obviously wax melted instantly. That's kind of predictable. This is not how you should put out a flammable liquid fire. Um, not really with a glove, and definitely not with a hose. But I got away with it on this occasion. I'm going to retry that test without the wax. Flip it over. Strangely, the tin which initially flexed downwards is now going to flex upwards, continuing in the same direction that it did the first time, which is really difficult to explain considering the heat's coming from the opposite direction. But this just illustrates the main problem with tin, which is that it's unstable under heat. Steel in high-rise constructions actually requires its own fireproofing. You have to insulate the steel from the fire to stop it from structural collapse. So that's something to keep in mind, that the tin might not be combustible, but it certainly can on occasion need its own fire resistance. It's Zincalume tin. The reason I've used that on this current tiny house is that it reflects heat. It reflects radiant heat quite well. You see how much I've heated it up there. It's not a particularly fair test. But it's what we're doing here really is replacing an enormous amount of radiant heat and an incredibly high ambient temperature from a bushfire. We're substituting that for an incredibly hot flame at a very close distance. So this is the same tin pinned to 9mm ply with a frame underneath it. Oh, that's me turning the gas bottle up a bit. Interestingly, we're at 140 psi with the gas. Main problem here is heat transfer through to the timber. There's no flame licking up the sides. That is the flame coming off the pine, where the red hot steel is touching it. It's got the same amount of flame there as the first test that I did, which was flame directly onto pine. So this performed well in terms of there a bit of melt, but generally, again, the pine stopped the radiant heat. They had stopped the heat transfer. That's our aluminium rivets. Now, we know aluminium melts, we saw it earlier. The only part of that rivet left was the steel insert, and it would definitely not have done its job. If your house was riveted together with aluminium, it would have come apart. This is a better system. In between the timber, we've got a Bradford insulation bat. There's lots of screws in it. There's steel rivets. It's in continuous span because it's got a center batten running through it. The insulation is 75mm thick. It's wedged into a 50mm gap. You can see I've tried to push it into the corners as much as possible as well. And here comes our heat. This test went very well. No complaints about this whatsoever. The heat transfer through to the inside was almost zero. And ignition was also very limited. So this is an effective method to build a house. Again, it's a combination of materials. Tin, insulation and timber all working together to stay stable, to stop heat transfer and to reduce the ignitability. This is only one half of the wall makeup for my tiny house. This is all on the outer side. On the inside there's another 70mm stud filled with earth wall insulation, and then the interior ply lining as well. So this is just this is less than half of the wall construction for my tiny house. but still very, very effective. The smoke eventually coming off the timber block underneath as a result of the radiant heat. As mentioned, the tin is reflective and it's doing its job here perfectly. It's reflecting heat back out. Something to consider when you're building your house, that any gardens around the outside could actually experience radiant heat from both the front of the fire and from the reflection of the house. So you can get a double hit if you're on the outside of the house. Very happy with this test. Also goes to show just how resilient the walls are compared to doors and windows. We're about to do the glass test. You can see a bit of flame licking around the side. The steel rivets are still there, they're still intact. Sorry, it's not great footage. And a bit of smoke leaking out. Got a few impurities in there as well. There was some ducting tape on the back of that insulation. Something to consider is that the tape that you're using on your insulation could be as much of a hazard as the rest of the construction combined. The impurities, even something as small as a sticker on the back of a piece of pine or on a product, could be a problem. Untoughened 3mm glass makes up the bulk of windows in Australia. Yeah, that's pretty predictable. It took about 30 seconds to flame. Toughened glass is what you want, which is what this is. Toughened and doubled. Double glazing is an insulative measure. It's not going to stop radiant heat, so I was a little bit surprised with how long this wax took to melt, but surprised in a good way for sure. Now this double glazed unit is flexing up, which is in contrast, no it's not, it's exactly the same as the untoughened glass prior, but the flex is an issue. This glass is allowed to move, there's no frame holding it still, and we'll see what happens in a second when you put a frame around it. It does change the test. I'm not suggesting you make your house flexible, that's not what I'm suggesting at all. Only that when testing materials, that the real life scenarios are taken into account as much as possible. Which is why the next test coming up is going to have a timber frame around it. The glass simply doesn't last as long. This unit here though was pretty impressive. Obviously a lot of heat coming through there at that point, and the wax is completely melted. A lot of smoke coming off the outside. Those edges really should be covered in installation, and the glass itself didn't break until now. Bang! Pops out the bottom because Fireman Tom hit it with a water hose, which seemed like a good idea at the time. But a common mistake people make too in the heat of a fire: spray the house down and cause breakage. Ironbark frame, ironbark's not going to burn. And most of the corners are rounded off to a fair extent. I did do this pretty quickly. It's not as neat as in the actual house, but it's the same construct. Steel trim, Silarub, which is a silicon resistant up to 290 degrees. The glass is argon filled, toughened 4mm and 8mm. Unfortunately 8mm was actually on top, not underneath as I intended to use it. But it's going to give us a good indication of how long these glasses last. Now that happened really quickly. That's the same 4mm toughened glass as in the last unit. The last unit it lasted for about 4 minutes of flame, and in this one it lasted about 1 minute. It's because it's in a frame and it's got nowhere to move. No flex is possible, so it shatters and pushes out. Right now we're about to see the second piece of glass shatter. It took certainly a lot longer, being 8mm, but it does go. It actually holds together. There it is. That's the shattering. You can't see it particularly well, but it has actually shattered into 1,000 pieces on top there. Um, Obviously, the wax is going to melt at that point, but what's impressive about this is that it's still protecting your house. For a unit which is not intended to have direct flame contact, the doors and windows on my houses have all got shutters, so she'd be protected from flame and radiant heat also. Um, but considering that these are designed to be behind shutters, this is doing quite well. The timber is not igniting. The rubber on the inside is obviously putting out a bit of flame, a bit of silicon flame there as well, but it doesn't catch fire. The interior glass remains, being being an 8mm toughened glass. And in a moment I'll try and smash that out, and it does actually take a bit of force. Um, yeah, a lot of flame hitting that, and still, as a unit, it's actually still intact. Um, I don't know, the timber around the outside unfortunately never catches fire. The regulations rate steel and aluminium construction ahead of timber. I've done repeated tests like this which show that it should really be the opposite way around. Timber is incredibly difficult to ignite and stable. Key there being stable. It also doesn't transfer heat through the inside, um, which is a huge problem, particularly painted steel. Steel could heat up on the outside, transfer through to the inside, and your paint could melt and become a huge smoke source on the inside of your house. As expected, most of that's still intact except for the glass panel. So glass always is going to be the weakest point in your house. Reduce the size and number of windows in your house if you want it to be fire resistant. It's still surprisingly difficult to punch out. The good thing about the toughened glass is it doesn't leave shards, unlike the untoughened, which goes into panes. This is it in use. There's magnesium board in the front. There's checker plate steel. That's silver top ash and ironbark being used for the door. It's a fire resistant door handle, which is all steel. There's a tin in continuous span with a lot of insulation packed behind it. Fireproof paint on this house. And again, fireproof paint, tin being used on this one here as well. And shutters on the windows. Those shutters are just made of steel. It's for a lower rating to protect the inside, which is much more flammable. Thanks for watching. Check out TC Tiny YouTube and Facebook.